Hi guys, welcome to this set of videos, and what we're going to be doing here in this set of videos is actually starting a new chapter, which is chapter 7, and what we're going to do here in this chapter is sort of go through everything having to do with exponential and logarithmic functions. Now we're going to start off chapter 7 by taking a look at the graphs of both exponential and logarithmic functions, and then later on in the chapter, in the coming sections, we'll begin to look at some of the algebra that you can do with exponential and logarithmic functions, and more importantly, sort of the modeling, the mathematical modeling that we can do with exponential and logarithmic functions. And we'll talk about why they are such good models for predicting natural phenomena when we get to those sections here in chapter 7. In fact, when we get to chapter 7, section 8, the entire section is essentially just solving a number of what we would call word problems or real life example problems, where we will model some sort of natural phenomenon using either an exponential or a logarithmic function. So really excited about this chapter. I enjoy exponentials and logarithms a lot, and we'll go ahead and get it started here in section 1 by taking a look at the graphs of these two algebraic functions, logarithms and exponentials. So let's go ahead and get a couple of objectives or learning targets to get us started, just something to sort of help us focus our learning as we go through these videos. The first thing you're going to want to be able to do by the time we get to the end of this set of videos in this section of notes is going to be graphing exponential functions and graphing exponential decay functions. All right, so we're going to do exponential growth and decay functions here in this section. We'll graph both of them. So let's go ahead and jump right into it and see how these go. What I've got for you here is just a little bit of information about graphing exponential growth functions. And the first thing I want to do here is make a real quick note that all of this, all right, everything listed here is if there are no transformations. So this is without transformations or no transformations. Now, we talked about, actually, we've done transformations in pretty much every chapter here in Algebra 2, starting back in Chapter 2 of Algebra 2. And when I'm talking about transformations, remember, I'm referring to the variables a, h, and k, where a will either vertically stretch or compress the graph, or will be a reflection across the x-axis. H will be a horizontal shift left or right, and k would be a vertical shift up or down. So when I say no transformations, what I mean is that A is just a positive 1, H is 0, and K is 0. So as long as there are no transformations, all of these general trends about exponential growth functions are going to be true. We'll talk about transformations on a later page. So let's go ahead and jump into some of these. Here we go, general trends. Highlight real quick for you. Has the general form y equals b to the x power. So here's what's going to happen. What we've got here in this chapter is now the exponent is the variable. B just represents some constant, and I tell you right here that b has to be a constant greater than 1. All right, we'll talk about why in just a second. So now, for the first time really kind of here in Algebra 2, we're looking at functions where the variable is the exponent, and our base, what we'll call the base of the exponential, is going to be the constant. A couple of things, just the general way that this graph is going to look, but I point out the most important trends right down here. It increases from left to right. You'll notice that that graph is exponentially increasing as you move from left to right on the coordinate plane. Again, as long as there's no transformations, that will always be true. Also, the x-axis is going to be your horizontal asymptote. Please notice that in the graph I've given you here, that line comes very, very close to, but will never touch the horizontal asymptote, which is the x-axis. Again, as long as there are no transformations. If I begin to change k and I shift that graph vertically up or down, then that's going to shift my horizontal asymptote. But as long as there's no transformations, the x-axis will always be our horizontal asymptote. And finally, this one, as long as there's no transformations, it doesn't matter what the base is. This b can be anything, 2, 3, 4, 10, a million. Doesn't matter. Anything to the first power, right? Or I'm sorry, anything to the 0 power is always going to be 1, which is why every single exponential function, every single one of them, as long as there's no other transformations, is going to go through the point 0, 1, every one of them. And we'll see that when we start doing a couple of example problems. Right? Now, real quick, I want to talk about this, and then we'll go on and do an example problem. And here's what I want to talk about. This idea of the exponential function, which is y equals b to the x, right? So b is some constant. My variable is now the exponent. And I've essentially got 3 options. I could have b being less, all right? It could be less than 1. I could have b, which we're going to talk about first, being greater than 1, and then my other option was b equal to 1, all right? So these are essentially my 3 options, okay? Now, what's going to happen is right away here in the first couple of example problems, we're going to talk about this option, where b is greater than 1. It's known as an exponential growth. This is going to be growth. After we talk about growth later on here in this set of notes, we're going to talk about what happens if b is less than 1, but greater than 0, all right? So b is essentially going to be a fraction, right? It'll be a decimal or a fraction, and this is what's going to be known as exponential decay. Okay? We'll talk about both of these. The one that will never happen, ever happen, is where the base is equal to 1. And here's the reason why. If my b were a 1, then I would have the function y equals 1 to the x power. Well, let's just think about this for a second. If I have y equals 1 to the x power and the x is the variable, well, 1 to any power, right? It doesn't matter what I plug in for x. 1 raised to any power is always going to be 1. What that means is you wind up with a graph that is the constant function at y equals 1. So you'd wind up with a graph running right through here. This is y equals 1, because 1 to any power is always going to be 1, right? So if you plug in x equals 1, 1 to the first is 1. X equals 2, well, 1 to the second is still 1, right? So what you wind up with is a constant function, which is really boring. It's not exponential. It has nothing to do with what's going on in this chapter. It's a constant function. We talked about it back in chapter 2. So you will never, ever have a situation where that base is equal to 1. So what we'll do here in this set of notes is talk about when b is greater than 1. Then we'll talk about when b is less than 1 to kind of finish things off. So head on over to the next page of the notes. We'll go ahead and get started with an example problem, and I'll meet you guys over there.